table can be used to recognize similarities and differences among the chemical elements. It can be used to identify the metals and nonmetals, as well as elements with characteristics of both: platinum, silicon, tungsten, lead. These and the other elements each have their own symbol and their own place on the periodic table. If you know an element's position on the periodic table, you can determine many of its chemical properties. You can predict the relative size of its atoms and know how it will react with other elements. It's the periodic recurrence of properties that gives the table its name. One of the first periodic tables was organized in 1869 by a scientist named Dmitri Mendeleev. He used cards to organize what he knew about the elements and came upon a grouping that shed light on other factors. Elements that fall in the same vertical column on the table have similar but not identical properties. These vertical columns are known as a group or family of elements. Metals, gases, transition elements, and rare earths each found themselves in groups when arranged by mass on the earliest versions of the table. Even undiscovered elements were identified by empty spaces in the chart. Later, when others arranged the elements according to atomic number, the grouping improved, and this is what's used today. And this, and this. Some elements are separated from the body of the table. This is really just for printing purposes, because the table would be awfully wide if they were left in their proper places. Let's look at the first row, or period of the table, which contains the two simplest elements, hydrogen and helium. Both are extremely light, colorless, odorless, and tasteless gases at room temperature, but their similarities end there. Together, these elements make up most of the universe. Roughly 9 out of every 10 atoms in the universe are hydrogen atoms, and most of the remainder are helium atoms. Hydrogen is the fuel that makes the sun and stars shine. At the extremely high temperatures and pressures within stars, hydrogen undergoes a nuclear reaction that releases tremendous amounts of energy and produces helium. Nuclear reactions involve changes in the tiny, positively charged nucleus in the center of the atom. The nucleus contains most of an atom's mass. Protons and neutrons within the nucleus are held together by strong nuclear forces. Unlike nuclear reactions, chemical reactions involve only negatively charged particles called electrons, found in the outer regions of the atom. Hydrogen atoms have atomic number 1, making them the simplest of all atoms, with a charge of +1 on the nucleus and a single electron in the space around it. In nearly all of its chemical reactions, hydrogen either loses its single electron to another atom or shares its electron with another atom. Chemists use dot structures to keep track of electrons in compounds and reactions. Hydrogen has just 1 electron, so its dot structure has just 1 dot. Helium, with symbol He, has 2 electrons, so it gets 2 dots. What's amazing is that extra dot, 1 single tiny electron, makes helium's chemistry completely different from hydrogen's. In fact, helium does not react with any other element under normal conditions. It is extremely stable chemically. On the other hand, hydrogen reacts with many other elements and forms many different compounds. Both of these elements in the first period have one energy level that can hold 2 electrons. When an energy level is full, it's stable. When an energy level is not full, it is unstable, and it is more likely to gain or lose electrons until it becomes stable. 2 hydrogen atoms can share their electrons to form a molecule. This molecule is much more stable than the hydrogen atoms were by themselves. In the molecule, each hydrogen atom has 2 electrons moving around its nucleus, exactly the same number of electrons as chemically stable helium. If we think of hydrogen's reactions as a drive to reach the stable 2-electron arrangement of helium, we can understand how the reaction of hydrogen and oxygen atoms form water, H2O. Oxygen atoms have 6 outer electrons, so their dot structure is drawn with 6 dots. Each hydrogen in the water molecule shares a pair of electrons with oxygen, so each has the stable 2-electron arrangement. Now let's look at the second period and how the properties of elements change across it. The trends we see in the second period generally hold across other periods too. The most obvious of these trends is a gradual transition from shiny, solid metals to gaseous nonmetals. Metals get harder and less reactive as we go from left to right across the table, and nonmetals get more reactive. Lithium, at the beginning of the second period, is the lightest and softest of all the metals. Lithium has to be stored under dry kerosene because it reacts with air and water. And it's soft enough that it can be cut with a knife. The next element, beryllium, is also a metal, but it's much less reactive than lithium and it's much harder. Beryllium is one of the most toxic elements. A metalloid is an element with a blend of metallic and non-metallic properties. Boron is a metalloid. Crystalline boron reflects light in a metallic way, but unlike metals, it's brittle. It can't be hammered into sheets and it doesn't conduct electricity or heat very well at room temperature. Electrons are shared between boron atoms, forming a network of bonds. This makes it much less reactive than beryllium and harder than almost all other elements. Carbon, the next element, is a nonmetal that can take on a variety of forms. Black slippery graphite, black sooty amorphous forms like lampblack, soccer ball-shaped clusters called fullerenes, and diamond, one of the hardest substances known. None of these forms are very reactive at room temperature. Carbon atoms can bond to one another indefinitely. The other elements only form short chains. The remaining elements in period 2, nitrogen, oxygen, fluorine, and neon, are nonmetals and gases at room temperature. Nitrogen has very low reactivity. Under normal conditions, nitrogen forms diatomic molecules. But oxygen, while also a gas that typically forms diatomic molecules, is very reactive. Fire, the most familiar of all chemical reactions, involves oxygen. Fluorine is an extremely reactive gas. It forms compounds with nearly every other element, sometimes explosively. It etches glass, eats through metal, and destroys living tissue. Neon, the last element in the second period, is also a nonmetal and a gas, but it is completely unreactive. How can we explain these patterns of behavior? And how can we explain the abrupt change from solid to gas that we see between the elements carbon and nitrogen? It's all about the arrangement of the electrons. The arrangement of electrons in second period atoms is more complex than in the first period. Second period atoms have a stable 2-electron helium core, with additional electrons placed outside in a second layer or shell. The outer shell is called the valence shell. Only electrons in the valence shell tend to be involved in chemical reactions. Let's go back to the table. The atomic number gives the total number of electrons in a neutral atom. Second period atoms have 2 electrons in the core and the remaining electrons in the valence shell. So here are the dot structures for all of the second period atoms. Helium and neon have full valence shells. They are chemically stable and are known as noble gases. It turns out that all of the elements below neon on the table are also considered noble gases, though a few of them do form compounds with fluorine and oxygen under extreme conditions. Every period on the table ends with a noble gas. With this information, can we explain any of the patterns seen? Remember, the most reactive elements are lithium and fluorine. There is a steady decline in reactivity across the period until we reach oxygen. The reactivity then increases until we reach neon, which is unreactive. Notice that the two most reactive elements, lithium and fluorine, are the ones that lie closest to a noble gas on the table. It may appear at first that lithium is quite far from a noble gas, so you might expect it not to be very reactive. But this is an illusion caused by the fact that we typically draw the periodic table as a flat grid because it's easier to print. In reality, the end of one period lines up to the beginning of the next. We can show this idea by rolling up the table so that the ends meet. "75% of all the elements are metals. Let's look for patterns in reactivity among them. The easier it is for atoms to lose electrons, the more reactive they will be. Group 1 elements are more reactive than Group 2 elements because their atoms lose electrons more easily. Why? It takes work to pull an electron away from the nucleus of an atom. The higher the positive charge on the nucleus, the more work it takes. Ionization energy is the energy required to pull an electron away from an isolated atom. On the rolled table, we can see that the metals in Group 1 and Group 2 can lose electrons to get the same number of electrons as the nearest noble gas. Atoms of Group 1 elements can lose one electron, forming cations with a charge of +1. Atoms of Group 2 elements have to lose 2 electrons, forming cations with a charge of +2. Let's look at the alkali metals of Group 1. They are so reactive that they are never found uncombined in nature. Pure samples have to be stored under oil or gas so they won't react and form compounds with air or water. One general dot structure and one electron configuration can be written to describe any of the alkali metals. Remember, the elements in Group 1 lose one electron to form cations. M stands for any alkali metal, and N is the number of the highest occupied energy level. They all react with water to form a metal hydroxide and hydrogen gas. Lithium reacts steadily with water. See the bubbles of hydrogen gas. Sodium reacts more violently. Notice the orange flame. Potassium ignites on contact with a violet flame. Looking at rubidium below potassium on the table, we would expect it to react even more violently, and it does. Like the alkali metals, Group 2 metals are reactive. Alkaline earth metals react readily with oxygen in the air to form a dull white oxide coating. Calcium is very hard and impossible to cut with a knife. Both barium and strontium are softer than calcium, but are still not easy to cut. Magnesium metal burns with a bright white light and is often used in flares. Group 2 elements react with water to form hydroxides and hydrogen gas, but much more slowly than the alkali metals. Magnesium reacts very slowly unless steam is used. Calcium is faster. Barium, which has the lowest ionization energy of the three, reacts more vigorously. Salts of the alkaline earth metals also emit strongly when heated in a flame. They are commonly used in fireworks displays. All of the alkaline earth metals are harder than the corresponding alkali metals. This also makes the alkaline earth metals melt and boil at much higher temperatures than the alkali metals. Why do metals occur on the left-hand side of the table? We've seen that lithium and beryllium lose electrons to attain a stable noble gas configuration. In fact, they lose electrons so easily that their atoms share valence electrons with all of their neighboring metal atoms. With all this sharing of electrons going on, metallic elements are essentially positive ions bound in a cloud or sea of valence electrons. This sea of electrons gives metals their characteristic properties. As we go across the table, the positive charge on the nucleus becomes greater and greater, and the atoms hang on to the valence electrons more and more tightly. By the time we reach boron, the electron C model no longer works. Boron is not a metal. Its valence electrons are held too tightly at room temperature to form an electron C. Boron does become more metallic at higher temperatures, and its ability to conduct electricity increases with temperature as well. Materials that behave this way are called semiconductors. They only conduct electricity at high temperatures. All are solid at room temperature. They conduct heat and electricity better than nonmetals, but not as well as metals. When a semiconductor like boron is heated, the boron atoms in the lattice begin to vibrate. Some of the covalent bonds break and are free to form an electron C. That explains why boron behaves more like a metal when it's hot. Boron is in group 13. One general dot structure and electron configuration can be used to describe all the elements in this group, sometimes called the aluminum group. In the 1800s, aluminum was so rare and expensive that Napoleon had a crown made out of the metal. Once an additive called cryolite was found to lower the melting point of the ore, it was a lot easier to get. The price plummeted and aluminum crowns were replaced with gold ones. All group 13 elements react to form oxides and halides, compounds like aluminum bromide. In this reaction, a tremendous amount of energy is released when the aluminum and bromine come together to form aluminum bromide. Other group 13 elements include indium. This can easily be bent and has a relatively low melting point, but not as low as gallium. It will melt in your hand. Thallium is an extremely toxic heavy metal. Granules of this element are stored underwater to contain any dangerous vapors that form. Why does the reactivity of metals increase going down the group? We can explain this trend in terms of increasing atomic size. Each new period on the table corresponds to the filling of a new shell of electrons around the nucleus. So the atoms get larger as we go down the table. The larger the atom, the farther away from the nucleus the valence electrons are. Electrons that are farther from the nucleus are not held as tightly. They are easier to remove in chemical reactions. This makes larger atoms, towards the bottom of the group, more reactive than the smaller atoms above. The elements in groups 3 to 12 are called the transition metals because they represent a gradual transition in properties between group 2 and group 13. These elements differ from those of all of the groups we've seen up until now in that they contain partially filled shells buried below the valence shell. These partially filled inner shells subtly affect the valence electrons, and so the chemistry of each element. All of these metals have similar valence shell configurations, so there usually is not as much variation in properties going from one column to another as there are in other parts of the table. When we come to the groups after the transition metals, we see much more variation in the behavior of elements within a group. We see a pronounced transition from nonmetals to metals within group 14. The group starts with carbon, a nonmetal, and continues with silicon and germanium, which are both metalloids, like boron, ending with the metals tin, lead, and the still unnamed element 114. Carbon is a nonmetal. Its valence electrons are too tightly bound to form an electron C. In its diamond form, carbon does not conduct electricity at all. All of the valence electrons are locked into strong covalent bonds. Each atom is connected by these bonds with each of its four nearest neighbors. The bonds lock each atom tightly in place, making diamond exceptionally hard. So why do we see nonmetals, metalloids, and metals in the same group in this part of the table? An element can behave like a metal only if its electrons are easily removed. As we go down a group, the atoms of an element get larger, and the valence electrons are pushed farther and farther away from the nucleus. The more distant electrons are from the nucleus, the easier they are to pull off, and the more metallic the behavior of the element will be. Elements become more and more metallic as we go down a group. This is exactly what happens in groups 13 to 16. Let's look at an example. Group 16 shows increasing metallic appearance from a colorless gas to yellow powder to a grayish metalloid to a metallic solid. We've seen that elements display an incredible range of behaviors. The periodic table arranges the elements so that we can recognize trends in element structure and reactivity using simple models. The location of an element on the table is based on the element's behavior, especially how it reacts with other elements. By studying the periodic table, we can see trends in the behavior of elements. Using the table to understand these trends gives us the ability to learn more about the chemical world around us and helps us predict what will happen next.